All right, so complex numbers, what are they? Where do we use them? Well, we use them in areas of mathematics, mechanical engineering, quantum mechanics. So branches of mathematics, apparently, that actually make, by working with imaginary or complex mathematics, it makes the calculus side of calculation somewhat easier. I guess the fundamental principle of a complex number is that we introduce an imaginary number, and that imaginary number is I, such that I squared equals -1. Okay, and I guess the most significant application of that is now all of a sudden we can evaluate the square root of negative numbers. So whenever a negative or the sign of an expression is impediment or a barrier to extending the math or continuing on with the math, we can introduce I squared, which is -1, and get away and remove that negativity. Okay. So by definition, a complex number, I squared equal to -1. A set of complex numbers form an expression a plus bi, where a is the real part of the number and bi is the imaginary component of the number. So I guess when we talk about our number system, and it sort of has it on the page above us, real numbers. Okay, so it extends our number system. So the form, as I said, of a complex number is a plus bi, noting that a and b are both real numbers. A and b, I should say. As I said, a represents the real part and is called res of z, re of z. For real, sort of makes sense. B represents the imaginary part, called the imaginary part of z, or im of z. Okay. If a is equal to 0, we just get left with bi, 0 plus bi. Obviously, that's an imaginary number. If b is equal to 0, then z is just equal to a, isn't it? And so we have a real number. So if you like, all real numbers are a subset of the complex field. It's just that the imaginary component happens to be 0. So let's just do some basic manipulations. Express negative root 49 in terms of I. Well, given that I squared equals -1, we could express that as root of 49i squared. Yeah, because the I squared is -1, and the square root of that is simply 7i. Example 2, what is the real component of -2 plus 3i? Well, the negative component of that is just -2. Yeah? The imaginary component of -1 plus 4i, well, the complex component is 4i, so the imaginary part of that is just 4. So that's really important. The imaginary component is not 4i, it's 4. So when we ask for the imaginary component of a complex number, it'll always give you a real answer. So just a few basic properties that kind of make sense if you think about it. I to the power of 1 is clearly I squared is -1. I cubed, that's just I squared times I, which is -I, and I to the 4, I squared times I squared, which is -1 by -1, which is 1. So any power of I will have one of those three results. And so you're just really looking at the where it is in relation to a factor of 4 or a multiple of 4. So I to the 4, as I said, I squared by I squared, which is equal to +1. I to the 5, I squared by I, which is just I. And in fact, obviously, you can start thinking it through. I to the 6 is I to the 4. So I to the 4 times I squared. And we know that I to the 4 is 1. And I squared is -1. I to the 7. I to the 4 by I to the 3. Which is I squared I, which is -1. Or -I. Yeah, so really what we're sort of highlighting here is that if we're a multiple of 4n, it's just going to be I to the 4, I to the 8, I to the 12, which will just take us back to 1. 4n plus 1 means I to the 4n is 1, and so we've got I left over. 4n plus 2 will leave you an I squared left over. 4n plus 3 will give you an I cubed, which will be an I squared I, which is negative I. Yeah, so it doesn't matter what we raise to the power of, the result has to be one of those four terms. So if we've got something like I to the 13, so if you like, I just sort of go straight to I to the 12 times I to the 1. I to the 12, multiple of 4, so it's just 1, so we get left with I. 2I to the 6 by negative 2I cubed. We just apply our negative 2 cubed, or we might just write it as that, I cubed. So common base, add the powers. 2 by negative 2I cubed is negative 2, add the powers to the 4. I to the 6 times I cubed is I to the 9. So that's negative 2 to the 4, I8 times I1. I8 is 1. So it's going to be negative 2 to the 4, isn't it? So what's that? Negative 16. Negative 16I. I squared by 2 by negative 3I. Well, I think we could expand it through, but I squared is just the same as negative 1 times 2 minus 3I. So I get negative 2 plus 3I. All right, so it's just remembering that property of I squared, that imaginary component. I to the 2019. Well, 2000 is divided by 4, so we know that that's going to be just 1. 19, which means 2016. 2016 is perfectly divisible by 4, so that's 1 times negative I, so it's minus I. I to the 220, same sort of thing, isn't it? So that's really just I to the, what is it, 2020. Oh. What's that, 504? 505. 505 times 4. So it's just an even factor of 4, even multiple of 4. So it's just going to be equal to 1. And obviously we can use our CAS to check these things. So you can see on the CAS there, we can just type in those values. What's really important to note, and it's a bit hard to read on the graphic there, is that I know this is a slightly different format of your CAS calculator, but the I symbol is under the pi button. Yeah, it's where we access our the pi sign. I'm just trying to think, exponential, those sorts of commands. It's not the I on the keyboard. Okay, completely different. All right, so it's just important about where we access it from. Okay, so when comparing complex numbers, the only way two complex numbers can be equal is if the real component equals real component and imaginary components equal the imaginary components. So, for example, the only way 3 plus 4i can equal a plus bi, a has to be 3 and b has to be 4. All right. So if we, in this kind of scenario here, we wanted to equate. For the left-hand side to equal the right-hand side, we knew 2a plus 3b has to be equal to the other real component, which is negative 1, and a minus 2b, which is the I component, so there's the imaginary component, has to be equal to the imaginary component on the left, which is 3. So what are we going to do there? Well, if we'll multiply by 2, or even negative 2, I guess. I can write negative 2a plus 4b equals negative 6. Add them together and we'll get 7b equals negative 7, so b equals negative 1. Sub it back in, I get a plus 2 equals 3, so a is equal to 1. Okay, so if I put those values into that expression there, I'll get 2 plus 3b, which is minus 3, plus a, which is 1, minus minus 2, which is plus 2i, which is minus 1 plus 3i, which is the same as the right-hand side. All right, so the properties of our complex numbers, as I mentioned, they're only equal if x is equal to a and y is equal to b. When we add complex numbers, we add the imaginary component. We add the real components. We add the imaginary components. So it's like for like, a bit like our vectors. We add the I component and the j component, imaginary and real. If we subtract, we subtract the respective components. Yeah, which I guess is just drawing that parallel with our vector addition and subtraction. So very briefly, if I'm going to add those two complex numbers, Z1 plus Z2, well, add the imaginary. So that's just equal to, it's equal to, add the real components, which is 3 plus 6, which is 9, 4i minus 10i minus 6i. And if I'm going to subtract those two numbers, I'm going to do Z1 minus Z2, so 3 minus 6, which is negative 3. And then I get 4i minus 10i, which is a plus, which is 14i. Okay, so I guess really by way of introduction, there's not a lot of comprehension. It's just knowing a few skills, a few definitions, and getting used to a very different branch of maths.